Greetings all, welcome back. Today I want to talk about another kind of first order differential equation which lends itself readily to integration, lends itself readily to solving just by the nature of its structure. That would be called a separable differential equation, first order differential equation, and there's sort of a standard form. Now this form is a little bit different than what's in the book, and we'll rectify that soon, but for right now, let's start with the following. Suppose we had a relatively general form for our differential equation, y prime equals some function of t and y. So now we know our independent variable, we know our dependent variable. We have our form. Suppose this guy is such that I can write my f of ty, my function on the right-hand side here, as a product of two functions, one of which is only a function of time, the independent variable, and the other is only a function of y, the dependent variable, the unknown function, the mathematical model. Okay? So let's suppose this guy is a product of two functions that can be written this way. This is helpful since then we can separate variables, and this facilitates solving. Okay, so at this point, if this is true, the ODE is called separable, and I'll write this in another color. Okay. And indeed, it's separable because of the way in which we can separate the variables. So given something like this, if we had a y prime, and we wanted to write that, and we could write that as g of t h of y, in essence, then we could actually write this so that we can put all of the t variables on one side, bring all the y variables, including y prime, on the other side. In essence, we've separated the variables. So I could easily then write this just by division as 1 over h of y, and I'll write my dy dt, my y prime this way, equals g of t. In essence, all the t's are over there, and all the dependent variable data is off on this side. Okay. Why is that interesting? Well, this is actually a function of time on this side. This guy's also a function of time, although it's sort of implicitly defined because we don't know what y is yet, but I know y is a function of time. I know h of y is then a function of time, and 1 over that is also a function of time, and its derivative with respect to t is a function of time. So both of these guys are functions of time here. Since this is equal to this, I could integrate at this particular point. And if I integrate, then I wind up with, on this particular side, 1 over h of y dy dt dt. And on the right-hand side, I get the integral of g of t dt. And it's pretty obvious to see that this right-hand side is just the antiderivative of the function g of t as a function of t. What's interesting about this guy on this side is that this guy is the antiderivative of 1 over h of y as a function of time. Okay? That's not so easy to see. That looks actually very complicated, but it's actually not. And this guy really, the entire differential equation can be solved by integration. Okay? And that's going to be useful for us. Now, one thing to keep in mind, and I'll note this over here, and we'll see what kind of room we have. This left-hand side So this piece right here, what do I want to say? This is in the form of a substitution method. Problem, right? If I wanted to rewrite that in a slightly different way, I could write this as the integral of 1 over h of y dy dt dt, and I'll write that in a slightly different form. Let's write that this way. 1 over h of u of x du of x dx dx. Okay. I'm changing the variables here because I want to basically show you how the structure of this particular works. This is a slightly different problem than this, but you can see that it's really the same kind of a problem. If I were to use a substitution, that y equals u of x, and then dy equals u prime of x dx, then this guy is nothing more than 1 over h of y. This is y prime here. This is, u prime of x. So this guy is nothing more than 1 over h of y dy. In other words, this guy really is the antiderivative of 1 over h of y as a function of time, but we can also look at it as just a function of y just due to that Calc 1 version, that substitution method. Okay? So really, to solve a differential equation of this type, when I can write this guy as a product of two functions, one a function of time and the other one a function of the variable y, if I can basically pull all the variables, time on one side and all the variables involving y on the other side, then if I integrate with respect to time, on this side I just get a standard integral. On this side, I can interpret this guy simply because of the substitution method as the antiderivative of 1 over h of y with respect to y. This is going to give me another expression involving y's. This is going to give me an expression involving t's. If at the end I can solve this guy for y, in other words, I can basically write this in such a way that I can find an expression y as a function of time, then I can use this to actually solve my differential equation. Okay. So just by virtue of us being able to separate variables allows us to basically integrate, and if we can do the integrals, then we can solve this differential equation, at least implicitly. So next time, we'll do some examples of this just to show you how this works. For now, thank you for listening, and we'll speak again very, very soon.